Hello and welcome to G Fun Facts Online. Today, we're going on a journey to the very heart of the atom to uncover the secrets of one of the most powerful and controversial technologies ever created by humanity. We're talking about nuclear enrichment. It's a process that unlocks the immense energy hidden inside the atomic nucleus, with massive implications for both global peace and devastating conflict. So how do we tap into this incredible power? Let's find out. It all starts with something called nuclear fission. Imagine an atom's nucleus as a tightly packed ball of protons and neutrons. In certain heavy elements, like uranium, this core is a bit unstable. Now, picture a tiny particle, a neutron, flying through space and smacking right into this uranium nucleus. The impact is so great that the nucleus splits apart into smaller pieces. This split releases a colossal amount of energy as heat and radiation. But here's the crucial part. It also releases more neutrons. These new neutrons can then fly off and split other nearby uranium atoms, which release more neutrons, which split more atoms. You get the picture. It's a self-sustaining chain reaction. If you control this reaction, you have a nuclear power plant, generating clean electricity. If you let it run wild, you have the terrifying destructive force of a nuclear weapon. So if we want to build a power plant, we just need some uranium, right? Well, nature throws a curveball at us. The uranium you dig out of the ground is mostly made of two types, or isotopes. Over 99% of it is something called uranium-238. The stuff we actually need for that chain reaction, uranium-235, makes up only a tiny 0.7%. The problem is, U-238 just doesn't split easily. It's the rare U-235 that's the key ingredient. To make nuclear fuel, we have to increase the percentage of U-235. This process is called enrichment. And it's incredibly difficult, because U-235 and U-238 are chemically identical. The only difference is that U-238 is just about 1% heavier. Every single method of enrichment is based on exploiting this tiny difference in mass. So how do you separate atoms based on a 1% weight difference? The first method, developed during the Manhattan Project, was called gaseous diffusion. It's a bit of a brute force approach. Scientists would turn uranium into a gas and force it through a series of filters with microscopic pores. Because the lighter U-235 gas molecules move a little bit faster, they have a slightly better chance of passing through the filter. But the effect is so small you have to repeat this process thousands of times in gigantic, energy-guzzling factories. It worked, but it was so inefficient that it's now considered a Cold War relic. Today, we use a much smarter method, the gas centrifuge. Imagine taking that same uranium gas and putting it inside a cylinder spinning at mind-boggling speeds. We're talking over 50,000 revolutions per minute. The intense centrifugal force flings the heavier U-238 atoms towards the outer wall of the cylinder, while the lighter U-235 atoms tend to gather closer to the center. You can then siphon off that U-235 rich gas from the middle and feed it into another centrifuge, and another, progressively increasing the concentration. These centrifuge plants are engineering marvels, and they use only a fraction of the electricity of the old diffusion plants, making them the global standard. But science never stops. The next frontier is laser enrichment. This sounds like science fiction, but it's real. Scientists use lasers that are tuned to a very specific frequency of light. This light only excites or ionizes the U-235 atoms, leaving the U-238 atoms alone. Once the U-235 atoms are tagged by the laser, they can be easily separated. This method promises to be even more efficient and could dramatically lower the cost of making nuclear fuel. Not all enriched uranium is the same. The level of enrichment determines what it can be used for. Most nuclear power plants run on what's called low-enriched uranium, or LEU, which has about 3 to 5% U-235. There's also a new type called high-assay low-enriched uranium, or HALEU, with up to 20% U-235, designed for advanced next-generation reactors. Once you get above 20%, you have highly enriched uranium, or HEU. This is used in some research reactors, to make medical isotopes, and to power nuclear submarines. And if you enrich uranium all the way to 90% or more, you get weapons-grade uranium, the key component for a nuclear bomb. The leftover material from this whole process, with very little U-235, is called depleted uranium. It's super dense, which makes it useful for things like radiation shielding and armor-piercing ammunition. This brings us to the heart of the controversy. The exact same technology, the centrifuges or the lasers, that can enrich uranium to 5% for a power plant can also, if you run it for longer, enrich it to 90% for a weapon. This is why it's called a dual-use technology, and why uranium enrichment is at the center of global politics and non-proliferation efforts. International bodies like the International Atomic Energy Agency, or IAEA, exist to inspect and verify that countries are using their nuclear programs for peaceful purposes only. It's a constant, high-stakes balancing act. Interestingly, after the Cold War, a program called Megatons to Megawatts took highly enriched uranium from dismantled Russian nuclear warheads, diluted it down to low-enriched uranium, and used it to generate electricity in American homes. A true example of turning swords into plowshares. The science of splitting the atom has taken us on an incredible journey, from a theoretical curiosity to a world-altering technology. Nuclear enrichment is a powerful testament to human ingenuity. As we look to the future, grappling with climate change and our ever-growing need for energy, nuclear power and the enrichment process that fuels it will remain a critical part of the conversation. It's a story of immense power, complex technology, and a profound responsibility that we all share in wielding the secrets of the atom. Thanks for listening to G Fun Facts Online.